Hello guys, welcome back to Maison African Motives, still on industrial electronics and for that is working on revisions. We are going to be focusing on the question paper which was written in April 2023. That is for the April 2023 exams. That is the one that you're going to focus on so that we see exactly what we're given and how are we supposed to attempt these typical questions. So let us check the first part as we see the instructions and information that you're supposed to understand. Answering of all the questions that you're given, read all the questions carefully and number the answers according to the numbering system used in this question paper. Write neatly and legibly. That is whatever that you are indicating must be clearly shown. All right, so we had the first part of our question, which was question number 1. That is on the superposition. The application of the superposition. Study the circuit diagram below and calculate the current flowing through the 7-ohm resistor. Take note, through the 7-ohm resistor using superposition. So we are supposed to apply the superposition theorem to calculate the current that is going to flow through the 7-ohm resistor, which is this one, R3. That is our 7-ohm resistor in this case. All right. So how can we attempt this typical question? That is the question that we are having. All right. So what you need, remember, according to the superposition, we are going to short circuit one of the voltages. What you need, we have got a voltage source here. So you short circuit maybe V2. You work with the V1, calculate the currents according to the branches that you're given. You must calculate the current that is going to flow through the 7-ohm resistor. You do the same thing if you are referring to short circuiting of V1. You calculate the currents that will flow and the current that is going to flow through the 7-ohm resistor. Then you combine your final answers at the end. All right, so let me explain this in calculation. So let us start with the V1 in this case. Let us see what is going to happen if we are to short circuit V1 in this circuit. This part is going to be a short circuit, this part here. So meaning to say, we are going to have our circuit at the end. All right, if you check, we said that is our question 1.1. We are going to short circuit V1, or we start with V2 depending with what you want. So in this case, let us start with V1. So we are going to short V1. By shorting V1, we calculate the current across the 7-ohm resistor. Calculate the current across, that is the current across the 7-ohm resistor. Across the 7-ohm resistor. So we're going to do the same thing with shorting of V2. Then we calculate again the current across the 7-ohm resistor. Then we combine our resultant at the end. All right, so this is what you're going to have. If we check according here, if these two resistors, they are in parallel, these two resistors, so you're going to have these two resistors in parallel and a short circuit of V1. So this is what you're going to have at the end. Remember, I say the two resistors that we had, which were in parallel. So let me just have a sketch here. You understand me later on. So I want you to actually understand what is happening here. So this is what you're supposed to do. We short circuit this part of V1. All right, it was like this. This is the part of the two resistors. If we short circuit this, we've got resistor R3. So we're going to have resistor R3 in this case. All right, so we are going to have a short at this point. That is where we had our V1. So we are just having a continuation. That is a short circuit, not an open circuit. Short circuit is continuous, all right? But remember also that there was a resistor R7 that was there. So you're going to consider that resistor R7, the one that you are focusing with. And this is a short circuit. It's a continuation. Open circuit, it will be a condition where another part is open like this. That's an open circuit. But here we need a short circuit. All right, like this, a continuation. So that's our 7-ohm resistor. Then later, we have got these two resistors and the V2. So this part is going to remain as it is. This part, you just have it as it is, the 3-ohm and the 3-ohm here and the 24-volt. All right, so this part, like I said, it is going to remain as it is. So we are going to have from this continuation, we are going to have a resistor here. That was our resistor R3, which is in parallel with another resistor, also R3 again in this case. So we've got R3, I mean 3 ohm, not R3, 3 ohm and 3 ohms. All right, so these are in parallel, but we have got a voltage source that is connected. So we are going to consider that our V2 like this. So this is what we are supposed to have at the end with our voltage source here, V2. So that is everything. You're going to write everything as it is, R1, R2, up to R4, and the V2, everything as it is. All right, so I'm going to indicate all those resistors as they were before. That is here. We had R1, which was 6 ohms. All right, so let me just try to reduce this one a little bit. All right, so we had R1 in this case, which was 6 ohms. We had R2, which was 4 ohms. So this was 4 ohms. And remember, this is now a short circuit. And we had R3, okay, let me cross check. Yeah, this is our R3 being 7 ohms. So that's our R3, the one that we are supposed to calculate. It's current R3 here being 7 ohm. And we had R4 being 3 ohms. The same with R5 here being 3 ohms, and our voltage V2, which is equivalent to 24 volts. All right. So why am I explaining this stage? Why am I actually redrawing? This is actually important so that you locate the flow of currents. But if we check here, we have got a complicated diagram. This is our first diagram that we reduced. But after having a short circuit of V1, we are still having a complicated circuit here. If you check here, these two, they're in parallel. We need to combine. These two also are in parallel. We need to combine. So even if we are to try by all means to check the current that is going to flow across the 7 ohm, it is difficult for us because here we are saying there's a flow of current from the voltage source, our positive. It branches to the parallel circuit. These two currents together, they combine again to this point. At this point, this current branches to the parallel circuit, another one to the 7 ohm. So as you can see, there are so many currents that we are dealing with in this case. So let us combine this into a parallel, this into a parallel. All right, so that's a parallel and parallel combination that we have. Remember in parallel that the total resistance in a parallel circuit is given as the product over the sum. So we're going to apply the product over the sum concept. So let us start with the first one. This one, I'm going to have this as the first parallel combination. So that means our RP1 is going to be the product of R1 and R2. So we are going to have R1 by R2 over the sum of R1 and R2. So that is going to give us the parallel combination. That is, you multiply 6 and the 4 ohm resistor. That is the product. So we've got 6 by 4 over the sum, which is 6 plus 4. All right, so let us check what are we going to have at the end from our calculator. If we simplify properly, this was going to give us something like 2,4 ohms. So this is 2,4 ohms. So this is the first parallel combination. But according to our diagram here, we also have a parallel combination here. This is our second part. So we're going to calculate again from the product over sum. So our second parallel combination consists of R4 and R5. So that is the product of R4 and R5 over the sum of R4 and R5. All right, so that will be the second parallel combination, which is 3 by 3 over 3 plus 3. So you're going to multiply 3 times 3 over 3 plus 3. All right, so if we combine this, we are going to obtain the total of this parallel combination, which is going to be 1,5. So we obtain 1,5 ohms. All right, and like I was saying, this was a much complicated circuit. Now we have combined these two resistors into a single circuit, meaning to say we are now having a single resistor here. We are now having a single resistor here. So we can have this diagram in this manner. I want you to see what you're going to have. Let me just try to have it aside so that we do not confuse ourselves. So like I said, we are now having these two resistors as a parallel combined together as a single resistor. So we can present this way. We've got a resistor here. All right. So that is these two resistors combined. Then this connection is parallel to this 7 ohm resistor. There's a 7 ohm resistor, this one. So we are going to have our 7 ohm resistor here. All right, so we are supposed to have this resistor maybe somewhere here, but writing this resistor here is simply the same. Here we are having a loop at this point. So if a resistor is at this point or is at this point, they are still in parallel because we've got a loop. They are not having the same currents because we are having a continuation. If you check here, there is going to be a continuation to these two resistors that we combined together, and we got RP2 here. So we are going to write as a single resistor now. So here we are going to have a single resistor, but also connected to a voltage source. So this is connected to a voltage source of 24 volts, which is our V2. So this is what you're going to have at the end. So we said the first parallel combination, this is our RP1, which is 2,4 ohms. So we are going to have our RP1 in this case. So this was our RP1, which is 2,4 ohms. And we have got the second parallel part that, sorry, this is our 7 ohm resistor. This one, our 7 ohm resistor. So this is our 7 ohm resistor, which was R3. This is the second parallel combination, this one from these two. So this is our RP2, and this is 1,5 ohms. We got this as 1,5 ohms. Our V2 being 24 volts. All right, so this is our V2. So how can we determine the current? As you can see, now we are having a less complicated diagram than the one that it was much complicated to work with. Here we can simply locate the flow of current and see how it is going to, according to the voltage source here, according to this is a positive, this is a negative. So our current is going to flow from the positive terminal, meaning to say this, we can refer it as our total current. Then this branches into this branch and also into this branch. According to your Kirchhoff's laws, we have this as the current across the 7 ohm. So this is the current across the 7 ohm. Then this is the other current. We can just name it as current 2, whatever way that you want. You can even name it as current X, whatever, as long you understand what you are doing. So what is important here is to find this current that is going to flow through the resistor, the 7 ohm resistor in this case. And how can we determine the current across the 7 ohm resistor? Depending with your knowledge of circuits, yes, you can actually work your resistors together at once, but if you are not actually understanding this, like you are starting and you are having some challenges, work it stage by stage. So what you can do is you locate here, these two are in parallel. If we check according to the flow of current, the current here and the current here are not the same. So meaning to say these two are in parallel. So we are going to combine them together to a single resistor. So meaning to say we have another parallel combination. Let's just say RP3, since we've got RP1, RP2. So we are going to have the third parallel combination, which is the product over sum of these two resistors. So this is the product over sum of RP1 times the R3. So this is R3, which is our 7 ohm, over the sum of RP1 plus R3 in this case. So that is going to give us the parallel combination, which we have RP1 being 2,4. So we're going to multiply 2,4 times the 7 ohm resistor over the sum, which is 2,4 plus the 7 ohm resistor. So this is going to give us RP3, the one that is in parallel. Then we can determine the total resistance and so forth and so forth. All right. So this is going to give us something, or let me just have it here. Okay, let me just have my calculator and see what we're gonna have here. I want us to see this properly, the product over sum. Yes, I had another part before, but here we're just going to have a fraction. So we can multiply 2,4 times 7. So you multiply times 7 over 2,4 plus a 7 like this. So this is going to give us 1, 1,787 to 3 decimal places. So that's 1,787. So we've got 1,787 ohms, which is the resistance that is of the parallel combination, this one. But if we check at the end, this is in series with the RP2 here. These will be in series, because if you check, you combined these two. So at the end, you're supposed to have a resistor like this. You're supposed to have this as your RP3. That is these two resistors that you combined. Connected, because this is the loop that we have here. These two, we combine them. It's now RP3 here. This is our RP3, the one that we got now. But now it's connected straight. It's just connected to the second parallel combination that we had, our RP2, which is 1,5. So if we check, what are we having at the end is simply a series combination that we are having here. These are in series. The current that flows here is the same as the current that is going to flow throughout. So meaning to say, in order for us to determine the total resistance so that we can calculate our current, we can use the series combination, meaning we are just going to add. So that means the total resistance in this case is going to be RP3, the one that we calculated, plus this resistor here, that was our RP2. That was our RP2, this one of 1,5. So we are going to add these two together. So that is RP2. So if we add, this is 1,787 plus RP2, the one that we got before, that was 1,5. So we have got 1,5. All right, so let us add and see what we are going to have. So you do not just, yes, you can use the exact values that you had, but you can now change this to the exact value that you have, which is 1,787 plus 1,5. So this will give us something like 3,287. So that is 3,287, 3,287 ohms as the total resistance. Why calculating the total resistance? By calculating the total resistance, this helps us now to find the total current here, which is this current. If we have got this current, then we can calculate the current across the 7 ohm resistor by using current divider rule. So meaning we can calculate the total current from there. Our total current is going to be from the total voltage. So our total current, which is not actual total, just current like this, is equal to the total voltage that we are referring to is V2. This is the voltage source of the circuit that we are now having. So we are referring to V2 over the total resistance. So that will be V2 over the total resistance, of which our V2 in this case is given as 24 volts. So we are going to divide 24 divided to the RT, which is 3,287. So we are going to obtain our total current in this case. All right, so if we divide this part, we are going to have a current of 7,301 amps. All right, remember, our focus is not about the total current. This is helping us to determine the current across the 7 ohm resistor. All right, so this current, I want us to take it back to the diagram so that you understand properly what I'm saying. When we replace this total current that we just calculated, remember our total current here, we said it's 7,301. So we have got 7,301 here as our current, 7,301 amps. With this current, how can we determine the current here flowing through the 7 ohm resistor, which is our R3? So if we check according to current divider rule, this current here is the one that is going to feed the 7 ohm, and it branches to the RP1. So meaning to say we can calculate the current across the 7 ohm resistor. Remember, the current divider rule states that, all right, so applying the current divider rule, we are saying the current across the 7 ohm resistor. This is the current across the 7 ohm resistor, but this is for our first circuit. This is for the first circuit, so you can just write it as 1 is equal to what you do for current. You use the opposite resistor. For the one that you're calculating, the current is this one. So you use the opposite resistor on top. So this is going to be RP1 over the sum of the resistors which the current is being shared to. It's being shared to these two branches. So you add those two resistors, that is RP1 plus R3 in this case, which is our 7 ohm resistor, times the total current, which is the one flowing or the one that is being shared between these two branches. So with this, we can substitute our values, our RP1 given as a 2,4 over the total of 2,4 plus the 7 ohm resistor. So we add the 7 ohm times the current that we calculate, which is we are referring to this as our total current for this circuit that we are having, which is 7,301. All right, so that's it, guys. From our calculator, we are going to obtain something like 1,864 amps. This is current. All right, so this is the current across the 7 ohm resistor. But for the first combination, when we short circuit V1, meaning we are going to do the same thing. Short circuit V2, you apply the same concept. So that is the stages. Then you check the flow of, also check the flow of current that we obtained. The current is flowing from this manner. From our circuit, the current is flowing in this manner. So we have to check with the second one, is it flowing in the same manner or it's opposing? So we are going to check that one later on. All right, so this is it for the first part. So let us now short circuit V1. So on this part, remember, we had to short V1 so that we can calculate the currents in the branches. And after shorting V1, we saw that we are going to have this combination like this and the parallel combination and so forth. So I want you to check what is going to happen from our circuit here. If we were to short V2, this is what we have, or this is where we have our V2 here. We were going to have this in connection here. We are now having this connected together, meaning to say these two resistors are going to remain as they are in parallel. These two resistors are going to remain as they are in parallel. So what we are going to do is to combine them, just like previously, we combined these two resistors in parallel. We combine these two resistors in parallel. So we are not going to repeat that. We are going to start with these two resistors already in parallel. This one that we had at this point, 2,4. And the second part in parallel also. All right, so I'm not going to start by having this from scratch because we calculated the parallel part before. So remember, this time we are to short V2. So we are going to short V2, then we calculate the currents as it is. All right. So as we saw, guys, we said the two resistors that we had before from here, the two resistors that we had are these ones that are in parallel. They are now combined. So if we combine these two resistors, meaning to say it is going to be in series with the V1. This parallel combination is going to be in series with the V1. All right, so we are going to have the first two resistors that we combined, which is our RP1 here, in series with the V1. So this is what you're going to have this time. The parallel combination that we had, which is our RP1 with the V1. This time we are referring to V1. Remember, we said we are going to short V2. So this is the first part of our circuit where I'm saying this is our RP1, the first parallel combination that we had of 2,4 ohms. And now V1 is part of your circuit, and your V1 was 12 volts in this case. The rest of the circuit is going to remain as it is, meaning to say this part is going to remain as it is here. We are going to remain with R3, the parallel combination, but now in short, this one, it's a short, but this one, we combined this before. But now we said we are shorting V2, so this is a series combination. It's just the resistor that we are having, the RP2, but in parallel with R3. So you're going to have R3 first, then these two resistors that we combined before, it will be somewhere here now as a single, as a just resistor with no voltage, because we said we are going to short V2. So this is what is going to happen. So meaning we are going to have R2 as it is, then that part of these two resistors. All right, so let me try to have it on our circuit diagram here. So very sorry, guys. I'm now having a lot of things. I just hope you understand what I'm saying. So here, we are going to have, okay, let me have where's our, okay, here is our RP2 here. So we are going to have our 7 ohm. This is where we had our 7 ohm resistor. Then we were supposed to have our resistor here with a short circuit. But having a short circuit, we can simply have our resistor like this because it's connected in series with a short circuit. So you can just have it like this. This was our RP2. If we still remember, we say this is our RP2, which is our RP2, the one that we calculated. We calculated these ones before, so we're not going to repeat, guys. That was 1,5 ohms. And this is our R3, which is the 7 ohm resistor. So this is the diagram that is now easier for you to locate your currents so that you can calculate, just like the previous part, you calculate the current across the 7 ohm resistor. So the purpose is again to calculate the current across the 7 ohm resistor, across the 7 ohm resistor. So meaning to say, according to our voltage source, there's a plus here, a negative, and current is going to flow this way. So we are going to have our current from V1 in the positive side. All right, so this we can just name maybe current, just this total current according to your positive here. It flows at this point. We are now having a junction. So just from your Kirchhoff's law, this is going to branch into this and another branch here. So this is the current across the 7 ohm resistor. But this is now for the second when we are talking about V2. So we are just going to have it as a 2 here. Then the other current, we can just name it current 2, no problem for that one. Whatever way that you want, even IX or whatever name that you can name it. So what we need is to calculate this current that is flowing across the 7 ohm resistor. And as we saw previously, that it was because of the total current that helped us to calculate this current using the current divider rule. So I'm not going to redraw this diagram because we had this from the first platform. So what we are going to simply have is to calculate the total resistance, as we saw that we need the total resistance where we said we have got a parallel combination here. So this is a parallel combination, but in series, whatever that you get, it is going to be in series with this resistor here. So meaning to say our total resistance actually here, let's write as the total resistance. Our total resistance is going to be the first resistor of RP1, which is in series to a parallel combination of these two resistors. So we are going to add these two in parallel. That is the 7 ohm, which is the R3, and this RP2. So we're going to have R3 times RP2 over the sum. Remember, product over sum over R3 plus RP2. So this will give us the total resistance. RP1 being 2,4 ohms plus the product over sum of these two resistors, R3, which is 7 ohms. So that's 7 times 1,5. So this will be 1,5 over the sum, 7 plus 1,5. All right, so this will give us the total resistance for this part of our circuit, not like for the whole circuit, but for this part of the circuit that we are dealing with, which is going to be 3, so we are going to obtain something like 3,635 ohms. So as this is our total resistance, what about the total current? Our total current can now be taken from the voltage source that we are given, which is V1 over the total resistance, which is our V1 being 12 volts over the total resistance of 3,635 ohms. So we are going to obtain our total current as 3,301 amps. So having this current, what about the current that will flow across the 7 ohm resistor? Our major part is the one flowing across the 7 ohm resistor, which is the second part now. So the current, using our current divider rule, I said you use the opposite because this is our current, the total current here, which is at this point. So we have got a current flowing towards this branch of 3,031. It branches into this branch and into another branch. So as we are focusing on the 7 ohm resistor, so you use the opposite resistor on top, which is RP2. So our formula is going to be RP2 on top over the sum of these two resistors, which is R3 plus RP2. So this will be RP2 times that total current. So we can substitute our values, RP2 being 1,5. So we've got our RP2 here being 1,5. So this will be 1,5 over the total resistance. We add these two, R3 being 7 ohms plus RP2 being 1,5 ohms times the total current. And our total current in this case, according to this branch, is 3,301 amps. So this is going to give us the current across the 7 ohm resistor. So the current across the 7 ohm resistor in this case is going to be 0,583 amps. So we're going to obtain the current of 0,583 amps. But if now we are to relate, because what I said, well, if you check properly, we had two combinations that we worked with. We worked with the first part where we had to short V1. If we check here, we had to short V1 and this combination on this part. When we short V1, we calculated the current across the 7 ohm resistor here. We calculated the current across the 7 ohm resistor, which we got this as 1,864. And the direction of current is this part here. If we check, this current is flowing down. This is the direction. So we are going to take this direction here, and see also with the second part where we had to short V2 at this part here. We had to short V2. So let me just have my my currents here. I think it's gonna be fine. All right. So when we had to short V2, this is what we are obtaining. Our currents are flowing in the same direction. As we can see, for the first combination, when we calculated the current across the 7 ohm resistor for the first part, we got a current of it was 1,864 amps. The direction, it was still flowing this way, going down. So if we check this part again, we are still having the same direction of the flow of current. We are still having the same direction. So on a condition like this, you are going to add your currents to determine the total current across the 7 ohm, which is the final current. Now you add. But if you are having a condition where these two are opposing, now let's say we are having the first current is going up, the second current is going down like this. On this case, you subtract. So if you've got a condition like this, you are going to subtract. So here it was going to be an addition that you're going to have. So meaning to say, therefore, the total current, so therefore, the current across the 7 ohm resistor, the current across the 7 ohm resistor, which is the total now, is the one that is we are going to add. That is the first part and the second part. So we're going to add the first current across the 7 ohm resistor, which is 1,864 plus the second current across the 7 ohm resistor that we calculated, which is 0,583. Since these are flowing in the same direction from different circuits, but they've got same direction. So that is why we have to add these. So that means, therefore, the current across the 7 ohm resistor is going to be given as 2,447 ohms. All right, so this is how we can apply our superposition theorem to calculate the current across any given part of the circuit, any given resistor, as long you are having a more complicated circuit. Reduce that complicated circuit into a circuit that into a normal part that you understand. From there, calculate your currents as usual. That is going to help you. Then combine them by checking the resistor. I mean, by checking the flow of current that you had before and on the final diagram. Are you having the same thing? If so, then you can now combine according to your addition or subtraction concept here. All right, so that is what we had on the first part of our question. The other part of the question, it was the define the following theorems in words: the superposition theorem, the Thevenin's theorem. All right, so let us start with the first part of our question, which is on 1.21, the superposition theorem, and that is 2 marks for that. All right, so in this case, I've got this part that I want you to check here, where we are given that it can be stated that in any linear multiple source network, the resultant current in any branch is the algebraic sum of the currents that would be replaced by each source acting separately. So that is what we saw in our previous calculations. We had to work with each source acting separate. Each source was actually separated from each. Then we combine our resultants later on. All right, so that was the first part of our question. Let's check the other part of the question that you are given. Now we are given to work on the Thevenin's theorem in this case, which is again 2 marks. So here we have got our application that we are given for Thevenin, that in any network that we are given can be viewed as a 2-terminal network and can be replaced by a single source of EMF, which is VTEV, in series with a resistor, which is a single resistance, which is referred to as RTEV. So remember, from a Thevenin, you calculate VTEV and ETEV, then you go to the equivalent circuit diagram for the Thevenin. So this is what we are simply having in this case. That was 2 marks just to explain what you understand about the Thevenin's theorem and superposition. All right, question 2, we are given to study the circuit diagram below and calculate the total current using J notation. We are supposed to apply the J notation. So what you need is to start, take note, you are given that you must study the circuit diagram, understand what is the information that you are given, how to relate this information. So this is our circuit diagram. And also you're supposed to use the J notation in this case to calculate the total current. We are referring to the total current. All right. So let us see what we have in this case. There was 12 marks in this case for everything. If we check here, we have got our voltage source. This is the AC. So AC does not affect, its plus or minus. So what we just need is to know the flow of current, which is in series here with R2 being 30 ohms. And we've got an inductor, L1 here, which is 110 millihenries. This is inductance. C1, our capacitor, 120 microfarad. C2, 160 microfarad, and R1 here being 50 ohms. So in order for us to have the current, what we need is to actually have this impedance. We have got these two a resistor and a capacitor. We combine, we calculate the impedance of this part, which will be our Z1. We have got a capacitor here. We are going to have this as our Z2. But these two being in parallel, they will be in series later on with this part. We have got R2 and the inductor here. So we're going to calculate, or we're going to have our Z3 here. So let us have first, I think that can help us to first locate our ZP, our Z1, Z2, Z3. Then we can check what is happening, because like I said, here, these two, they are in parallel. If we check Z1 and Z2, these two are in parallel. So how are we going to have our Z1? We understand that from the resistor and capacitor, Z1 can be given as R minus JXC. If it is a capacitor, if we have an inductor, then we've got a plus, where XC is our capacitive reactance. So we need capacitive reactance, which is XC. Where are we going to find our XC? From the capacitor. So here we are going to use the formula for XC, which is equal to 1 over 2 pi FC. So we have got our values, that is 1 over 2 pi from your calculator times the frequency measured in hertz. So our frequency is 50. So that's 50 times the capacitance. In this case, our capacitance, which is C2 of 160 microfarad, that's 10 times 10, 160 times 10 to the exponent of -6. All right, so we can have our XC in this case. Our XC is going to be something like 19,894. So that's 894 ohms in this case. But like I said, here we are now calculating the impedance. So it's a combination of the resistor and the capacitive reactance, but with a negative using J notation. So resistor R1 is 50 ohms. So this is going to be 50 ohms minus J XC, which is 19,894 ohms. All right, so this is what you're going to have this part measured in ohms. So like I said previously, that whenever you are referring to impedance, you do not know what is going to happen later on. So it is best for you to have a conversion in each and every case, to have your impedance in a rectangular form, at the same time to have your impedance in a polar form. So remember, we've got two formats that we have, the rectangular and the polar form. So here we have got in rectangular form, so we are going to convert to polar form. So we also need the same Z1, but in polar form. All right, so Z1 in polar form, remember guys what I said, you simply need your calculator. From your calculator, you can give the value of Z1 here by just changing to polar, that is shift to polar form here. Then we've got 50, so we're going to press our value, that is 50. We separate this, that is shift. We move to this comma here, that's negative. So the J part is carrying a negative. So you use the negative on your calculator, negative 19,894 like this. So we close, we can convert. So we are given R. Remember, in polar form, we've got R angle of theta. So our R is 53,812. So we are going to have 53,812 angle of our theta. So our theta from our calculator, we are also given, this is our theta. If we move here, we are going to have our theta, negative 21,697. So this is going to change into a 7. So that will be negative 21,697 degrees. All right. So this will be another expression that we can use, or that we can give for Z1. So all this part is representing our Z1, but only that we have got it in rectangular form. Also, we have got our Z1 in polar form. Like I said, you do not know what is going to happen later on. So it is best for you to have this in both formats. All right, with the Z1, we move on to Z2. Z2, we just have a capacitor. We do not have a resistor. So if we were to find our Z2, normally it was supposed to be like this. Remember, I said the formula. If you are given a capacitor, our Z2 was supposed to be given as, that is the resistance minus JXC. So we do not have the resistance. So meaning to say our resistance is given as 0 minus JXC, meaning we need the capacitive reactance from the frequency, from the capacitance that we are given. So we can calculate our XC from there. Okay, let me just use this one. So remember I said XC is equal to 1 over 2 pi FC. So that's 1 over 2 pi times the frequency of 50 hertz times C, our capacitance 120 microfarads. That's 120 times 10 to the exponent of -6. So we are going to obtain our XC. In this case, our XC is going to be 26,526 ohms. All right, so that's here we can combine now. We have got our XC, which is 26,526. So everything here is in ohms. That is our XC. So this is what we have in a rectangular form. So we are giving the value of XC, which is in rectangular form. So we can also convert this. We do not know what is going to happen later on. So it is best for us to just convert also our Z2 to a polar form. Having in polar form, we understand that this is a purely capacitive circuit. So we are going to have this at an angle of 90 degrees. But if you do not understand this, still use your calculator. Your calculator does not care about this. It gives you direct the answer that you're looking for. That is shift 4 in this case. We've got shift to this one. So that is our first part, that is a 0 in this case. We separate these two. Negative 26, we just write as it is. Negative 26, comma, 525, we close this bracket. So this is going to give us R being 26,526, not changing. So this will be 26,526. And the angle of theta, as I say, this is going to be at negative 90 degrees. So our theta there is negative 90 degrees. It's a purely capacitive path that we are taking. So this will be at 90 degrees, but having negative, it's like a capacitor that carries a negative. So this will be a negative also on your angle. So that is what we have, our second impedance in ohms. So like I said, this is just the same Z2, our second impedance, but it only that we are having in both formats, in a rectangular form and in polar form. Let it just be like that so that it helps you. Okay, so let us just finish about our impedances so that we just calculate the total at once. So let us move on to Z3. Z3 is a combination of R2 and an inductor this time. So meaning to say our Z3 is going to be the resistance plus JXL. There's an inductor this time. It will be a plus JXL capacitor minus JXC. So we need to calculate XL because we've got the resistor. So our XL in this case is going to be taken from this formula. Remember that XL is equivalent to 2 pi FL. So that means we can substitute into the formula, that's 2 pi times the frequency of 50 hertz. So we've got 50 hertz times our inductance, which is, take note, 110 milli. This is millihenry, so it's 110 times 10 to the exponent of -3. So that is going to give us our XL. All right, so let us just try and see what you're going to have from our calculator. We want to properly have this together. So this is 2 pi times the frequency of 50 times 110. So this is 110 times 10 to the exponent of -3, like this. All right. So this is 11 pi, which is as a decimal, it will be 34,5575, which will be 558. So we are going to obtain this as 34,558, which is in ohms. So having, all right, so, okay, I didn't even share this part of the screen. I think we're not even seeing this part. All right, so this is what I'm trying to say. 2 pi here times 50 times 110 times 10 to the exponent of -3. This is what you're going to have. So this will change here to an 8. All right, I think we have this together. All right, so this will be our XL, meaning to say we are going to have our Z3 at the end as Z3 is equal to the resistance that we are referring is 30 ohms. So that is 30 plus JXL, our XL, the one that we got from our calculator, which is 34,558. So this is what we have for Z3 in ohms. Okay, so still you have the same thing. We convert just like previously, guys. I want you to convert to polar form. Just use your calculator. You are going to obtain something like 45. That will be 45,763 angle of 49,039. So make sure that you perfect this. I want you to perfect this. Give me the exact value like this one. That is in ohms. So just like previously, we have our Z3 in both formats, rectangular and in polar form. So like I said, you do not know what is going to happen later on. Just have in both formats, just for the sake of calculations later on. So let us see what we are going to have. Remember, our question is to calculate the total current. So we have the impedance first, Z1, Z2, Z3. So let me redraw this diagram and see what it simply means. What it simply means, so that you properly see what we are going to do here. It simply means that, remember, we had Z1 and Z2, we combined. It's like a resistor like this. This is your Z1. We combined Z2. We combined Z3. This is where we had our Z3 here, which is connected to a voltage source like this. So if we check, these two are going to be combined together in parallel. Then after being combined in parallel, our circuit was supposed to be like this. The one that we are having here in series with our voltage source with the parallel combination. So this will be in series now. So meaning to say we can be able to calculate the total impedance by adding these two, the parallel combination that we got and this one that we were having before. So this is what you're simply having. So now we are using which part now, because we said we've got the parallel combination of Z1 and Z2 according to the name, to the naming part that I did here. I say this is my Z1 and this is my Z2. So I'm going to have product over sum, then add that one to Z3, which will be our ZT. All right. So let us start by the product over sum of Z1 and Z2. All right. So let us start by finding the parallel combination ZP. So in parallel, we are going to apply product. Remember, that is product over the sum, which is very, very important to note. So we said we've got Z1 and Z2 over Z1 plus Z2. Those formats that I was presenting before, this is where now the formats are very, very important. Noting that the first part, the product, we are multiplying. So whenever you're multiplying, it is best to multiply in polar form. We are talking about the J notation here, but it's best for you to multiply in polar form. Addition, it's best for us to have addition in rectangular form. So meaning to say, for Z1 and Z2, for the top part, we are going to take them in polar form because it's best for us to have them for multiplication in polar form. Multiplication and division, it is best for you to do your calculations in polar form. So Z1, so let us have our Z1. So we're going to take our Z1 here in polar form, not in rectangular form. So this is our Z1. We take this one in polar form, which is 53,813 angle of minus 21,697. This is one that you're going to take. So it's Z1 and Z2, this one in polar form. So you multiply these two in polar form. All right, so let us multiply and see what we are going to have. So it's very, very important that you note this part. All right. So like I said, Z1, it's 53,183. So this was 53,812, sorry. Angle of minus 21,67, 21,697 degrees. So it's the product. We're meaning to say we are multiplying to this Z2, but multiplying to Z2 simply means we can just open a bracket. So it's multiplying to Z2. Also, Z2 must be polar form. So Z2, we are taking our Z2, this one in polar form, which is 26,526 angle of minus 90 degrees. So this is going to be multiplied over the sum. So like I said, for the sum, okay, let me just use this one so that we can just differentiate. So the sum of these now, you are going to have in rectangular form. So we are going to take Z1 in polar form, Z2 in rectangular form, Z2 in rectangular form. So this is your Z1 here in rectangular form, 50 minus J19,89 for this one. That's our rectangular form. So you're going to take the first Z1. So our Z1 in rectangular form was 50 minus J 19,894 plus Z2 in rectangular form. Again, our Z2 here in rectangular form, that's 0 minus J, so you just take this as it is, or you can just write 0, no problem, or you can just write 0 minus J 26,562. All right, so this is what you're going to have. So let us combine and see what we're going to have at the end. In a polar form, like I said, it's best for us to multiply because multiplication, you simply multiply the modulus to get the moduli together. That is this part and this part outside of these angles that you're given. Remember, this is an angle, this is an angle. So you multiply these together. That is 53,812 and 26,526. which is going to be 1427, 417. Then the angles, when you are multiplying in polar form for the angles, you add for multiplication. Subtraction is when you are dividing. So when it's like this, you add. So we are going to add negative 21,697 degrees to negative 90 degrees. So this is what you're going to do. So if we add, we are going to obtain negative 111,697 degrees. All right. So that is what we have. Then what about the addition in rectangular form? Why preferring adding in rectangular form? Because you simply add the real terms together. So here we are simply going to add our real terms together, 50 and 0. That is going to be 50. We add here, this is just combined, minus 19,894 minus this part. So minus this, we are going to obtain a minus there. That's minus J 46. So we are going to obtain 46, all right, that is 46,42. All right, 46,42. So that's negative 19,894 minus 26,526. All right, so this is what we have. But now we need to combine to find this ZP1, which is the first parallel combination. But if we check, we have a combination that is combined parallel. I mean, the polar form and the rectangular form. So what can we do? We are now referring to a division. So a division, it's best for us to deal with in polar form. So if it is that way, that it is best for us to deal with the division in polar form, it means we can change our denominator here into the polar form because the first part is already in polar form. So we are going to change our denominator is the one that we are going to change to polar form. So this will remain as it is, 142.7, 417 angle of minus 11,697 degrees. All right, everything over this in polar form. So like I said, guys, from our calculator, just use your calculator, shift pole, you as it is, you get your R there. If you get your R, it is going to be 68,226 angle of negative 42,874 degrees. All right, so this is what you're going to obtain from the polar form. Now you are having the resultant for a polar form combination. You are dividing in polar form. So the best thing is that you can divide the moduli together. These terms out of these angles, you can divide them together. So if we divide these two, we are going to obtain 20, so that's 20,922. Then for the angles, this part of the angles, we are dividing in polar form, so we subtract the angles. So that's minus 111,697 degrees minus, we subtract this angle of minus 40. So it's a minus already. So if we subtract minus 42,874 degrees, take note, it is going to be a minus and a minus, which is a plus. So this will give us something like negative 68, negative 68,823 degrees. All right, so this is our parallel combination. This is the parallel combination, which is in polar form. So each and every answer that you have, you do not know what's going to happen with our parallel combination, but in this case we know because we said the first parallel combination has to be added here from our diagram. If we check here from our diagram, we say this is our first parallel combination, these two. So whatever parallel combination that you get here must be added to this Z3. So that means in order for us to add, like I said, addition is best to be done in rectangular form. So it is best for you to convert your P1, the first parallel combination that we got here, to rectangular form also. You have your answers in both formats. All right, so let us convert this to rectangular form. So we just need our calculator. All right, so let me share back so that we can see again our screen so that we can do this to rectangular. So to rectangular form this time, it's again the same thing. shift, but you are to rectangular form. So you go to this one, rectangular form here, a negative. So you press your values 20, 922, separate this by shift, negative. Don't forget the negative. So it's negative 68, 823 like this. All right. So don't forget that negative. So this will give us 7,558. So we are going to have this as 7,558. Then let us check, is it going to be a plus or a minus? So here you've got the value of x and the value of y. So y is a negative. Remember, this is rectangular form with a j. So there is a negative. So it's negative j. That number that we are given here, which is 19,509. So we're going to have 19,509. So this is where how we can have our Z in both formats, the polar form and also in rectangular form. So this is our first part of our calculation in order to have our total resistance, our total impedance. So having ZP1, what is going to be the total impedance now? So remember, our total impedance, it is supposed to be equal to, we take it from this side, we calculated these two, remember? We calculated these two in parallel, Z1 and Z2. All right. I don't want it to go. I want this part here. All right. So we calculated Z1 here and Z2 in parallel. After that, we can see that there is a Z3 that I said it is going to be in series. So we're going to add this in series because these are now combined to a single like this. So this will be in series. So meaning to say we are going to add Z3 so that we calculate the total. And this is our Z3. Addition is best in rectangular form. So Z3, we are going to take this part in rectangular form. 30 plus J, 34. So this is the one that I'm going to use and add to the parallel combination. All right, so let us take this value. Let us take our value here. All right, so this is where on this part, this is where I need my ZT. So remember our value, guys, for Z3. So it said it is going to be, our ZT total is going to be Z3 plus the parallel combination that we got. So our Z3 in rectangular form, so we are talking about Z3, which was given as 30. Okay, this is equal to 30 plus J, 34. That was 34,558. Then add ZP1, our ZP1 in rectangular form. So we're going to add 7,558 minus J, 19,509. All right. So if we add in rectangular form, like I said, you add the real terms together, meaning to say 30 and 7,58. This part is going to be added together, which is going to give us 37,558. The imaginary part, the part with a J, is going to be combined together. So this is positive 34. So it's 34 minus 19,509. So 34 minus 19, is going to give us a positive. So that will be a positive J. 15, we are going to obtain 15,049. So this is our total impedance in ohms. And with this total impedance, again, it is best for us to convert this to polar form. I think now we are used, guys, to convert to polar form. So if you convert to polar form, you are going to obtain 40,461 angle of 21,835 degrees. All right, so this will be our total impedance. In this case, we've got our total impedance in both formats. That is rectangular. That is the rectangular and the polar form. So with this total impedance, we can obtain our total current, because we know that our total current is given as V, that is the total voltage over the total impedance. So here, let us have our total current. So our total current, like I said, that is the total voltage over the total impedance. The total voltage in polar form, because we are dividing, it's best for us to have this in polar. That is in polar form. That is the best way for us to divide in polar form. So if we can have this in polar form, that means we are now having the final answer. All right, so let us consider our VT, the total voltage here. According to our circuit, our V is at 250 volts. The angle that we are going to have, it will be at 0 degrees. So we're going to take 250 degrees, the angle at 0 degrees. All right, so this is what we are going to have. All right, VT here. All right, so let us have into our formula. So this is going to be VT. So our total current is going to be the total voltage of 250 volts at an angle of 0 degrees divided to the total impedance in polar form. And our total impedance in polar form was 40,461 angle of 21,835 degrees. All right, so this is going to give us the total current. That's in polar form. Remember, I said in polar form, you divide the numbers together. That is the moduli together. So it's 250 divided by 40,461, which is going to give us 6,179. Then for the angles, I said you subtract angles in polar form, you subtract. So it's 0 minus this, which is going to give us negative 21,835 degrees. All right, so this is current, which is measured in amps. So is there a need for me now to change this to a rectangular form? Once you have got your total current, there's no need for you to waste much of your time changing this to rectangular form and so forth, as long you have got your current in any presentation. The format that we have been working with is the most useful part. Is we're using the J notation to have this current. So it's not about to say your current, you have to convert back. No, you can leave your current at this. So this was going to be our total current from our simplification. These are the stages which are very, very, very important. Very, very important. As you can see, it's a lot. It's actually a lot. All you need is to play around with your calculator. Know the conversion. If you know how to convert with your calculator direct from rectangular to polar form, polar to rectangular, like I was illustrating, that will be the nicest way or the easiest way that is going to help us. All right, so that was our question 2. Let us check the other part of our question in this case, which was question 3. All right, question 3, we were given in this case to explain the following terms, just to explain what you understand by these terms. All right, 3.11, that is donor doping. What do we understand by the term donor doping in this case? All right, so let us see what we have got in this case. Let us see what we got for these ones. All right, so let us check. Let me just share the other part of the screen. Just want to share this screen again here. All right, sorry for that, guys. All right, no problem. So here we are given to explain the following terms. We've got donor doping in this case. So remember, these two types of doping, they are actually asked in both of them. So the donor doping is the process of generating that is free electrons in this case. So let us just have as the process. All right, the process of generating. So there's a generation there. So that is the process of generating. That is generating free electrons. We're talking about free electrons. That is the most important part. Then acceptor doping. Now, this is the process of generating holes. So this part, we are talking about generating holes. So this is the process, a process of generating holes in this case. All right, so these are the two that you're having, and 2 marks for that. 2 marks, 2 marks, which is actually a lot. All right, then the question 3.2, list 4 characteristics of a Zener diode. What are the characteristics of a Zener diode, which is 4 marks for that. So I've got a lot of applications that we can have. All we need is to choose which one is going to be best for us or in our simplification in this part. All right, so we've got for a Zener diode, that is it is a silicon junction diode that is doped to obtain a unique characteristic that it will not break down in the reverse bias condition if it is used within the limits of its specifications, and also it will contain a steady voltage across the diode in the reverse bias condition. It behaves like an ordinary junction diode in the forward bias condition, and also when a Zener voltage is exceeded, the avalanche point will be reached. A small reverse current flows in the reverse bias condition before the Zener reference value is reached. In the Zener area, a relatively large current flows through the diode. So these were the conditions that we could have worked with. Just pick any there or any four. All right, then 3.2, we are given a calculation that we are supposed to take here, where we asked you to calculate the suitable value of the series resistor if a 20 milliamp current flows through a Zener diode of 12 volts when connected to a 15-volt DC supply. All right, let us check what we have according. We have got, we want to calculate the suitable series resistance given the current and so forth. All right, so remember from our formula for calculating the series resistor, like we do not have the series resistor in this case. All right, so this is 3.3. All right, we do not have the series resistor, but we are given that here a current of 20 milliamps flows through the Zener diode. So this is our minimum current, the Zener current in this case, which is given as 20 milliamps. And there is a voltage across the Zener diode of 12 volts, and also the voltage across the DC, which is our Vin. So you've got two voltages here. The voltage across the Zener diode, which is given as 12 volts, and also the voltage across the sub, which is the Vin, which is given as 15 volts. So remember that to calculate the resistance across, which is the series resistor in this case, that is going to be added in our circuit, we are going to use the formula RS is equal to Vin minus the voltage across the Zener diode, everything over the current across the Zener diode minus the current across the load in this case. So this is the Zener mean current. So we have got these values in this case. So what you simply need is to substitute in order to calculate our RS. So meaning to say RS is going to be Vin, which is 15 volts. So we're going to have 15 minus the voltage across the Zener diode, which is 10 volts, everything over IZ mean, which is the minimum Zener current that we have of 20 milliamps. So that is 20 times 10 to the exponent of -3 minus the current across the load. We do, for this one, we do not have the current across the load, so that will be equal to 0. So in this case, we are going to use this as a 0. So that means we have the value of the series resistor. Our series resistor is going to be 250 ohms. So that is how we could have calculated this resistance, that is the resistor, the series resistor to be used in connection with this part. All right, so that was our question 3. The whole of question 3 having 11 marks. All right, so that's 11 marks. Then question 4, we were given to differentiate between a full wave voltage, full wave bridge circuit and a full wave center tap circuit. What are the differences between these two? So take note, guys, we need the differences. All right, so this is what I want you to have. So here we've got a bridge circuit. Remember, it's a full wave, but talking about a bridge circuit and a center tap. So a bridge circuit, it makes use of two diodes. It can function without the help of any transformer. Then a center tap, it makes use of 4 diodes. It cannot operate without the help of a transformer. So these were the best that we have according to our syllabus, guys. This is what they require you to actually have. So it's best for you to memorize on these to differentiate these two. All right, then 4.2, we are given a transformer that is used as a step down from 240 volts to 30 volts at frequency of 50 hertz. The secondary of the transformer is connected to a rectifier, and the rectifier is then connected to a capacitor filter. The capacitor is a value of 120 microfarad and a load resistor of 200 ohms. So this is on a half-wave rectifier. 4.21, you're asked to calculate the following: the output voltage and the output current in the half-wave rectifier is used. All right, that is the first part of a half-wave. What is going to be the output voltage, output current? All right, let us take our information and see what we have got in this case. Remember, we have got the input, which is a step. This one is a step down from a voltage of 240 to a voltage of 30 volts, which means at 30 volts, we are now having our VRMS there at 30 volts, having a frequency of 50 hertz. Then we have got the capacitor value of 120 microfarad. So this is 120 microfarad with a load resistor in this case of 200 ohms. So this is what we have. And if this is used as a center tap, how can we calculate, all right, how can we calculate the output voltage? That is the first thing, which is our output voltage in this case is, okay, so we are going to have as a half-wave rectifier. So that is the first part. So the output voltage that we are referring is our VDC in this case. And from our formula, our VDC can be calculated from VM. This can be calculated from VM, which is equivalent to VM over 1 plus, remember, this is going to be 1 over 2 pi FCL, 2 pi, and now we are not having pi, we've got frequency, so it will be 2 FC RL, all right, 2 FC RL. So this can give us the voltage, the output, but we do not have VM. This one, we do not have VM. So where can we obtain our VM from? From the VRMS that we are given here. VM, remember that VM is equivalent to the square root of 2 times VRMS. All right, so this will be the square root of 2 times 30 volts. So you multiply to 30 volts. So if we multiply, this will be something like 42,426 volts. All right, so having this VM, we can substitute here. As you can see, our formula is direct substitution, VM being 42,426, everything over 1 plus 1 over, that's 1 over F. Our frequency we are given, this is at 50 hertz. So we've got a frequency at 50 hertz times the capacitance. Here, our capacitance is 120 microfarad, which is 120 times 10 to the exponent of -6 times RL. Our RL here is 200 ohms. So we are going to multiply to 200 ohms. All right. So this is a single part divided from this 400 divided by this, which means we are going to have our VDC as 29,948 volts. All right. So this is how we can have our output voltage. And having the output voltage, it is going to be easier for us to calculate the output current. Remember, we are also told to calculate the output current. So from the output voltage and the resistance that we have, our total current for the DC, the output is going to be the VDC over the load resistor. So remember, our load resistor here is 200 ohms, and we calculated VDC. We say this is 29,948 divided to the resistance of 200 ohms. So this can give us the output current, which is now a DC current. All right, so that will be something like 0,14974, something like that. So we can round off to 3 decimal place. That's 1, 2, 3. 7, change this 9 into a 0. We give a 1 here, that will be a 5. So this will be something like 0,15 amps. All right, so that is the current output current that you're going to have, focusing with this from the VDC that we calculated as we are viewing this, or as we check this as a half wave rectifier. So the only part that we have is on our formula. So this will be 2F CRL. If it is a full wave, then this will be 4F. We just multiply by 2. All right, so I'm going to write the formula later on. So let us check what we are given now. We are given the output voltage and the output current if a full wave rectifier is used. So like I said, for a full wave, you simply, this VDC is just going to be multiplied. So this is what you're going to have, guys. All right, so let me just write this. This is now 4.22. All right, let me use this one, 4.22. So now we are using this as a full wave rectifier. So this part, we already calculated our VM, so we're not going to repeat that. We are just going to have our formula for the output now. Our formula for the output for VEC is going to be given as VM. So this will be VM over 1 plus 1 over. So this will be 2 times 2F. So this one was 2. So this one will be 2 times 2F CRL, which is a 4 now. So that means we are just substituting here. VM, we already calculate our VM. This one is not changing, which was 42,426, everything over 1 plus. So 2 times 2 here, which is 4. So this is the only part that changes. So it is going to be 1 over 4 times your frequency. This part remains as it is, nothing changed there. So that will be 50 times your capacitance, which is 120 times 10 to the exponent of -6 times your resistance RL, which is 200 ohms. So everything remains as it is. So this will be our VDC. So take note, this is when it is a full wave on 4.22. So that means our voltage, output voltage in this case, is going to be something like 35,11. So our output voltage, all right, is going to be 35,11. VDC is going to be 35,111 volts. All right, so this is how we can calculate it under a full wave. But if you check, it's not about the total voltage, it's also about the output voltage, the output current. So our output current is IDC, like I said, is simply the voltage current that you determine, the voltage source, the voltage that you get from the DC over the resistance from our load resistor. The load resistor is at the output at the DC. So that means we are going to have our VDC from the full wave, which we got as 35,111, everything over RL. Remember, our RL was 200 ohms. So we divide to 200 ohms. So this is going to give us the current on the output of 0,176 amps. So that is our IDC when it is used as a full wave. So the question is to understand between when it is used as a full wave rectifier and when it is used as a half wave rectifier. So this is the formula that you're going to use. All right, so that was our question on the question 4, having a total of 12 marks. Then we have got question number 5. All right, so let's check what we have on question number 5 in this case, where we are given transistor output characteristics show the relationship between VC, IC, and IB. That is what we are given to say whenever we're dealing with transistors, they show us these characteristics. So the question is, name and explain 3 important regions to consider in the output characteristics. Okay, what are the 3 things that we need to consider on the characteristics, but for the output in this case? All right, so let me show you guys what we have got in this case. So on the output, you have got the issue of the cutoff. In this case, the cutoff region, the collector and emitter junction are both reverse biased, resulting in almost no collector current. Then we have got the saturation region where both junctions are forward biased. Then the active region, the base emitter junction is forward biased, while the base collector junction is reverse biased. So this is where we have what we have on the active region. All right, so that was our question 5.1. 5.2, we are given that the output of an amplifier changes from 3 volts to 7 volts and a current of 2 milliamps to 10 milliamps. Calculate the dynamic impedance in this case. So the dynamic impedance is simply the like our output impedance, which we can write as R out is simply the change in voltage over the change in current, just like current over voltage over current gives us impedance. But now we're talking about the change, which is V2 minus V1. So you're going to have V2 minus V1 over I2 minus I1, which is simply output minus input. Output minus input. All right, so that is our voltage. In this case, we have got V2, 7 minus 3. So that's 7 minus 3 over I2 minus I1, which is 10 milliamps minus 2 milliamps. So 10 milliamps, that is to the exponent of 3. 10 times 10 to the exponent of negative 3 minus I1, which is 2 milliamps, 2 times 10 to the exponent of negative 3. So this is going to give us R out in this case, which is the output impedance, which is 500 ohms. Simply the change in voltage over the change in current. All right, so that was 5.2. 5.3, list 3 examples of push-pull amplifiers. What are push-pull amplifiers? What are the examples that we have in relevance to our syllabus? What do we have? Okay, so this is what we have. We've got the non-complementary class B push-pull. We've got the symmetrical push-pull class AB. We have got the complementary symmetrical push-pull class B, and the complementary system push-pull of class AB. All right, so these are the classes that we have, and according to this, it was just to list any 3 examples. So meaning to say from those 4, just any 3 of your choice that you think is the best. That was supposed to be our answer in that case. All right, then we've got question number 6, where we are given a summing amplifier having these values R1, R2, R3, and RF. And the input voltage is V1, V2 is not known. We are given V3 and V out. Calculate the value of the unknown resistor V2. All right, so let us check what we have in this case on 6.1. So if we consider in this case, this is a summing amplifier, guys. As we know, this is actually, let us just have a sketch here. So we know that our amplifier is supposed to have the terminals entering our amplifier, that is R1, R2, and R3 combined together. So this is what you're going to have entering our amplifier, but having a feedback. Also, we are having a feedback here. So this is what we have, negative, positive to our feedback. Then it goes to the output. All right, so from this point, it's now to the output. This is how we understand our diagram in this case. This is what we have. So we are given the first part. If we check, we have got the first resistor, the second, we have second resistor, third one, V1, we do not have V2, and we've got V3. And we also have RF and the output. So what you simply need is to ask yourself, if I'm using a summing amplifier, what is the formula that I was supposed to use to calculate the voltage out, because I am given the output voltage? From the output voltage, how are we supposed to have? We know that our formula is supposed to be given as V out is equivalent to minus RF into V1, that is V1 over R1. So we're going to have V1 over R1 plus V2 over R2. So we're going to have V2 over R2 plus V3 over R3. So if you are to check here, we have our V out. So you can substitute our V out. In this case, we are given our V out 6,14. So 6,14 is equal to minus RF. So that's a negative, our RF, which is RF, that is 35K. So this is 35,000. So that will be 35,000. Okay, into V1, our V1, we are given 3.5 volts. So this is 3.5 over R1, our R1, which is 8K. So that is 8,000 plus V2 is the one that is unknown. We do not know V2. So that's V2 over R2. Our R2 is 15K ohms, which is 15,000 plus V3. We have our V3 8.5. So that's 8.5 over R3, which is 25K. So this is 25,000. By just writing this, we can see that we have formulated a formula, we have formulated an equation that we can use in this case to solve for the unknown value, which is our V2 in this case. So how can we calculate our V2 depending with your combination? What you can simply do, let us just have this part. We can. I'm just going to write the first stage as it is. 6.14 is equal to negative 35,000 into these brackets. I want you to add the first part and the last part. This one we do not have any unknown, so you can combine these together. This will give us, if we add this, we are going to obtain something like 7.775 times 10 to the exponent of a negative 4. Okay, plus on this part, we have got V2. So this is V2 over 15,000, V2 over 15,000. All right. So what we can do, we can expand our brackets. In this case, 6.14 is equal to minus 35,000 multiplies this part. So it's minus 35,000 times this first part of 7.75. This part, if you multiply, we are going to obtain negative 27.2125, something like that. All right. Then you do the same thing with minus 35,000. You multiply. So you multiply this one as 1 over 15,000 like this. Negative 35,000 times 1 over 15,000. So if you multiply, you are going to obtain negative 2.333 and so on, which is V2. So what you're going to do is to make V2 the subject. Then we can calculate that value of V2. So here we can transpose this to the other side. It becomes a positive. It was a negative. So it is going to be a positive 6.14 plus 27.2125 is equal to negative 2.333 V2. So to find V2, we can divide by negative 2.333. Both sides, whatever that you get here, you divide by negative 2.333. All right, so this is going to give us V2, which is actually a negative from your simplification. If you simplify this whole part here, we are going to have our V2 as a negative, which is something like negative 14.296. But our answer for the voltage, this V2, is a positive. You're going to take the modulus of it, which is 14.296 as a positive. V out can be a negative, but this input is always a positive. So you take the magnitude of that answer that you obtained as a positive. All right. So this is the unknown value of V2 in this summing amplifier that we had. So these are the calculations. Just go back to the formula for the output of a summing amplifier. You substitute everything as you saw your circuit here. Just need also to know, even sometimes they might ask you to just draw a diagram to show these circuits. All right. 6.2, which op amp is used without a feedback? So which one that he has got no feedback at all? So that one is it's a comparator. Okay, so you just need to know these ones. That's a comparator. Then 6.2, draw a square input waveforms and output waveforms which are supplied with the following. All right, so the first one, it's an integrator. What are the input waveforms? But it must be square input. All right, square input. All right, so this is what we are going to have in this case for an integrator. If we are dealing with an integrator, this is our input and output. In this case, we are going to have our V in this case for the output as a square wave. Then our output, this is what you're going to have just like a triangular, like a sawtooth, okay? So we've got input and output waves of an integrator with the versus time in this case. So this is the time axis with the voltage. Remember, voltage goes together with the time. Then the other part of our question, which is 6.32, is for a differentiator. In this case, how are we going to have our differentiator? So our differentiator taken as our V in. Remember, our V in is still a square wave in this case. Then this is how we are going to have our output with looked like for a full cycle in this case. So that is the input and the output. We are going to have our waveforms when you're dealing with a differentiator in this case. So that was just 9 marks for question 6, everything 9 marks, which is actually a lot in exam. This is actually a lot. Then question 7, we are asked to explain the working principle of an LA SCR. What are the working principles in this case? What do you understand in the principle of operation? Whenever you're dealing with the principle of operation, all you need is to specify everything as you are given. All right. So here we have got the last is a silicon controlled rectifier that conducts when the gate is exposed to light. The gate still operates as a normal gate that is in an SCR, but in many cases is left what? Disconnected. In many cases, this is left disconnected. So that is what we have on the operation. Then the second part, these are just theory questions. 7.2, to list disadvantages of using a triac. What are the disadvantages that we might have or on the involvement of a triac? In this case, we are going to have the gate is control over conduction once the triac is turned on, as it is in case of an what? SCR. The triac is a very high switching delay. The triac is not suitable for DC power application. So meaning to say we are limited when we are to deal with a DC in this case. All right, then 7.3, choose the correct word or words that is going from those given in brackets. So you're given these ones. The characteristic curve of ASCR, which is the last, is the same as that of we've got a triac, a diac, and the SCR in this case. So what is it that is the same? Remember, we are told before that these two, they go hand in hand with an SCR, all right? So this is the same as SCR. So that was our first one. 7.32, an amplifier, all right, is a closed loop. Okay, a closed loop has got a feedback. So with a feedback in this case, in a closed loop system, an automatic controller must. So an automatic controller is supposed to sense that the controlled condition is not at the desired value. So it's supposed to sense. And 7.32, is used to adjust the physical quantity on which the value of the controlled condition depends on the block diagram of a closed loop. So this is a correcting signal in this case. All right. Then we have got 7.35. During the positive or half or negative half cycle, complete full cycle, or whatever that you have of the input signal, the SCR will turn on, during which that is during the positive, it turns on the positive half cycle. So that is when it is going to turn on. So that is part of the question. Then we've got question 8. Again, we have to choose from these two. Okay, we are supposed to answer with these words: capacitive, inductive, or resistive. So we are given Angular displacement, what is it about? So an angular displacement, that is capacitive. So this is capacitive. Same with the liquid level, guys. This one, remember, that's your capacity. It's under capacitive. Then a potentiometer, that is resistive. We are talking about resistance more. This one is resistive. All right, then draw a strain gauge used as a Wheatstone bridge. We are supposed to draw a strain gauge. How can we present a strain gauge but used as a Wheatstone bridge? Okay, so this is what I'm having here that you can use. Taking here R1, R3, R2, and R3. These are the strain gauge stress, and these are the strain gauge. So we are just given a half bridge strain gauge circuit that we can use as a bridge. So knowing that the strain gauge is included in your bridge, the resistors, two resistors, then we can put a strain gauge on top, another strain gauge with a voltmeter, which is a potentiometer in this case. All right, we've got a voltmeter at the center. Then 8.3, briefly explain the operating principle of a photodiode. We are given the type of a diode that we are dealing with, which is a photodiode. Remember that a photodiode is operated under reverse bias condition. When light falls on the PN, electron pairs are created, which create an increase the availability of minor carriers. The minor carriers under reverse bias condition causes an increase in the leakage current as light intensity increases. That is, the leakage current increases and the diode become more conductive. So that is where what we have on a photodiode. Remember, a photodiode just like a normal diode, but this one we are going to have it taking in light like that. That's a photodiode. All right, so that is what we were given on this part. And question number 9. Okay, so that's question 8, 11 marks. Then question number 9, which is the last part of our question. All right, that was actually a lot. All right, let's see what we got. Question number 9.1, name 2 choices of synchronization provided for on the front panel of a cathode ray or oscilloscope. Okay, the choices of synchronization provided for on the front panel of a cathode ray oscilloscope. All right, what are the choices that we presented? Okay, so we have got in this case the internal. Remember, we've got the internal. All right, we also work with the external and the line. All right, so I've got the external and the line. So these are some of the, from these 3, we can just pick 2 to answer this question. 9.2, explain voltage scale and time scale. Voltage scale and time scale. What are the actually, we are not asked the difference. We are just asked to explain them. Okay, so a voltage scale can be given is the vertical axis of an oscilloscope screen. The time scale is the horizontal axis of an oscilloscope screen. So when you are having a screen, the horizontal axis, that's your time scale. The voltage scale is taken from the vertical in this case. All right, so this is what we had. Let us check the other part of our question 7. That is question 9.2. On question 9.2, we are given to okay, that is the one that we're actually working with. 9.3, no, so this thing of not marking. All right, 9.3, explain the following information which appears on the front panel of an oscilloscope. Okay, we talked about the choices before. Now we want the information that appears. So we have got the first thing, which is the focus. We've got the intensity. We've got the volts per in this case. So what is it that we are going to have? So let us start with the first part, which is the focus. So for the focus, what we have is that it is the adjustment that allows the operator to produce a small clear spot or thin line when measuring. That is what we have in this case for the focus. Then the other part, we are given is for the intensity in this case. So for the intensity, it determines the brightness of the spot on the display. So whenever we're working on your display, it determines the brightness of the spot on the display. Then we have got the volts per dev, which is it adjusts the amplitude of the waveform, since you're talking about the voltage part. All right, so these are the some of the things that we might need in our revisions, the knowledge that we might need in our revisions in this case, which helps us in answering of questions. Let us continue to revise as much questions as we can. So that was our question paper, having a total of 100 marks. All you need is to work on more questions, revise on your theory, revise on your theory, revise on your calculations. Everything has to be revised. This is industrial electronics info. You need to work on both. Know that you are strong in calculations. Also, you're strong on the theory part, so that you can be able to obtain at least half of the paper. So that's what you had, guys, from Maison African Motives, working on industrial electronics info. Till we meet again.